And to round out the session, we have Jiangyi Liu, who's going to be presenting automated ambiguity detection in layout-sensitive grammars.
Hi, everyone. It's my honor to have the chance to give the talk here. My name is Jiangyi Liu, and I collaborated with Fengmin Zhu on this paper. I'm a first-year PhD student in the University of Wisconsin-Madison. Since I was an undergraduate student in Tsinghua University, I've been working on this project with focuses on aiding layout-sensitive grammar design. I've talked enough about myself, so let's start by having a look at the layout-sensitive grammars. So what are layout-sensitive grammars? By definition, it's a type of grammar where indentations and white spaces affect the parsing process. The layout in its name means positioning of the tokens, which depends on the white space symbols. This is quite different from the context-free grammars, where white spaces are discarded in the tokenization phase. The following Python program illustrates how layout affects parsing. On the left side, only the second print statement is executed, while on the right side, both prints are not executed since they both belong to the if body whose guard condition is false. Python is a language defined with layout-sensitive grammars, and therefore, indentations play a big role in the semantics of those programs. Layout-sensitive grammars have a wide application. It has been used in many modern programming languages, including Haskell, Python, and F#. What's more, newer versions of existing languages, like Scala 3, are also trying to integrate this feature. However, not all programming languages are layout-sensitive. There are many of them that can be expressed solely with context-free grammars. So why using this type of grammar? Shouldn't context-free grammars be enough to express the programming languages? A main reason would be that it encourages writing elegant and stylized programs. In fact, one reason why Python chose this type of grammar is that it enhances readability. As in the end of Python, we have readability counts. Python is known for its bracket-free and semicolon-free coding style. Many Python programmers are so into this style that they try to apply such a style to other languages, and here's a case of this. Since this programmer hates the semicolons here, they moved those disturbing symbols to the end of each line. It is so unnatural that this case seems a little bit silly. However, that programmer would certainly love Scala 3. The Java code can be rewritten into the following Scala code. Scala used to do not support layout-sensitive grammars, but it supports using indentation to denote the control flow structures now. It looks much cleaner and easier to read, isn't it? Suppose that you are trying to build your own programming language that uses layout-sensitive grammars. This is indeed favorable given that there's already languages like Scala 3 is already doing so. When it comes to such a serious use, we have to take possible ambiguity into consideration. That is because in most cases, you don't want the programs in your language to be ambiguous, since it makes those programs no longer reliable. Only if you rule out the ambiguous grammars can programs become solid and clear. But how can we check if a grammar is ambiguous? It might be tempting to try identifying and eliminating ambiguity manually, but it's really hard to do so. Here, we present a fragment of layout-sensitive grammar used to describe the statement blocks. There are two production rules out there, and the block symbol is the star symbol. Note that we extended the EBNF to include the annotations like this little double pipe symbol that acts as the layout constraints.
Sorry, can you go just a tiny bit to the left with the E to be in the frame?
Oh, like this?
Yeah.
Okay. So the second rule is rather straightforward. A statement can either be a not token or a do token followed by another block. The first rule, however, includes a layout constraint, which we call aligned claim class. To begin with, it's a claim class, which means the terms within should occur one or more times. What's more, it requires every line to be aligned. That is starting from the same column as shown in this graph. So how many of you think this grammar is ambiguous? If you think so, can you provide a counterexample? Please raise your hands if you think so. Okay, maybe many of you have guessed that it's an ambiguous grammar. Here we have a sentence which acts as a counterexample. Below it is what the tokenizer generates for the layout-sensitive parsers. Note that the tokenizer's output now contains the line and column numbers that may be used by the parser. We also listed out the two parse trees here. In the first tree, both null ops belong to the do block. However, in the second tree, only the first null op token belongs to the do block. In this corner case, the cause of the ambiguity is the fact that all tokens are aligned with each other. So what did we learn from this example? Manually determining ambiguity is rather hard, and we should switch to automated ways instead. However, an instant question would be that, isn't the ambiguity of grammars undecidable? The answer is a big yes, and we should find an incomplete but useful way instead. Let's introduce bounded ambiguity checking, which is such an incomplete but useful way. It's a weaker notion of standard ambiguity, which checks that there's no ambiguous sentence under a certain length k. The idea of bounded ambiguity checking comes from Isaacsen's work on CFG ambiguity detection. The next question would be, how do we solve the weekend problem? Isaacsen then created an encoding called BAMB, which we listed here, and proved in their paper that it is equivalent to bounded ambiguity. We first started by directly extending the BAMB encoding to include the layout constraints, like the line and column relations, and switched to the use of SMT solvers instead. But then we found that a direct extension of their method would be not enough. We started by trying to formalize the direct extension encoding with the cock-proof assistant. However, we failed to prove the soundness of their work in cock. By inspecting the failing proof goals, we determined that the direct extension to be unsound. To bridge the gap, we strengthened it into a new concept called local ambiguity. It repaired the unsoundness of the BAMB encoding on layout-sensitive grammars by introducing extra conditions and makes the encoding sound again. Starting from the concept of local ambiguity, we created the following benchmark. The following framework, sorry. To begin with, we created an ambiguity checker in Python, which first encodes the local ambiguity condition in SMT formula and then invokes the Z3 solver to check if there's an ambiguous sentence within the given length bound k. We've also formalized our theory in cock and proved the equivalence between local ambiguity and the standard bounded ambiguity here. We also showed in cock that the SMT encoding is analogous to the local ambiguity condition. In the rest of the talk, we focus on how we achieved the local ambiguity condition here. For the other parts, you can refer to the paper for details. Recall that we started from the previous work by Isaacsen and strengthened their encoding to adapt to layout-sensitive grammars. We've already mentioned that BAMB alone is not enough for layout-sensitive grammars. To go into more details, let's first illustrate Isaacsen's BAMB condition with the following graph. BAMB tries to find the two subtrees with roots labeled A that differs on the first level. In short, BAMB finds ambiguous subtrees instead of full ambiguous trees on the right side. After those subtrees on the left side are constructed by the encoding, the full parse tree wouldn't need to be produced from those two subtrees T1 and T2. To recover the complete ambiguous sentence, we need to complete the missing parts like the TL and the TR subtrees. Isaacsen has shown in their paper that such a completion can always be done for context-free grammars. However, this doesn't apply to layout-sensitive ones. So let's start with an example grammar here. This grammar is not ambiguous, and it has 6 production rules and starts with the symbol S. The rule S to A requires that all tokens derived from A lie on the same line. A derives to B1 and B2. B1 and B1 contains an alignment restriction. Alignment here means that the first token on both sides should lie on the same column. Intuitively speaking, B1 can only produce a multi-line sentence. However, given that S only permits all tokens to be on the same line, B1 can be seen as actually a disabled production rule that will never apply. Hence, the grammar can never be ambiguous. However, the following sentence satisfies the BAMB encoding. It contains two seeds on the same column of two lines. By inspecting the BMB encoding, we found out that it detected the ambiguous subtrees T1 and T2, which are both valid. Hence, it concludes the ambiguity of this grammar. However, when we try to recover the full parse tree from the subtrees, we found out that the full trees are actually invalid. This is because the rule starting from B1 should never be used, as it's in conflict with the first production rule. Therefore, this example is a false positive for ambiguity. So why this can happen with layout-sensitive grammars? If we only focus on the subtrees, even if we find ambiguous ones, we cannot be certain that those subtrees can be extended into a complete parse tree. Like shown in the graph, in the previous graph for BMB, the existing complete trees may not be valid at all. But recall that Isaacson has proved in their papers that for CFGs we can always do such an extension, since there won't be things like the layout constraints that stands out in the way. To resolve this, we need to drop the subtrees that do not correspond to the full parse trees. This can be seen as the subtree being unreachable from the star symbol S, and those unreachable ones should be dropped in the encoding to ensure its soundness. So we start by reviewing the classic reachability definition on context-free grammars. A non-terminal X is reachable in the context-free grammar if there exists a derivation starts from S that produces it. Note that when we define reachability here for context-free grammars, we do not consider specific sentence W. That is because reachability for context-free grammars can be decided by the grammar structure alone. But that's not the case for layout-sensitive grammars, because whether a layout predicate is satisfied actually depends on the sentence that is currently being parsed. I'll intuitively explain how we adapt reachability to the layout-sensitive grammars. Suppose that we already have a parse tree on the left-hand side, starting from the non-terminal A and derives the sentence W. We want to know if this parse tree corresponds to a complete parse tree that starts from the star symbol S. If we come to the figure here, we can see that it corresponds to whether we can find the red parse, like TL and TR, and the parse above it, the one starting from S, that completes the subtree T. If so, there would exist a path that goes from S to A on the full parse tree. Hence, we have the name reachability here. This wouldn't be needed for CFGs, since a subtree in CFG can always be trivially completed. However, here, we have already shown that for layout-sensitive grammars, the layout constraint on the path from S to A can actually make the completed parse tree invalid if any of the constraints on that path is not satisfied. With the reachability condition in hand, we can actually define our own equivalent notion for ambiguity. Local ambiguity is defined as the conjunction of BMB and reachability. We then proved in Quark that the local ambiguity condition is an equivalent condition to bounded ambiguity. Now that we have local ambiguity, we can translate that into SMT formula. It discusses whether the ambiguous sentence is empty and respectively encodes the BMB and the reachability conditions for each case. We've also proved the correctness of the given encoding and showing its bounded soundness and completeness. Soundness says that any sentence defined is indeed ambiguous, while completeness says that if there exists an ambiguous sentence of a certainness k, then the SMT formula phi k is satisfiable. What are the take-home messages from this talk? To begin with, ambiguity is quite important in language design. Sometimes people can actually avoid ambiguity detection by choosing the correct fragment like LL or LR grammars. When this is not possible, as in the case of layout-sensitive grammars, we have to have a way of automatically detect the ambiguity. The second point is about the proof assistants. They are actually quite useful and can surely help you develop a robust theory when you are working with SMT or set solvers. Last but not least, SMT solvers can also be applied to formal language research, as we've shown in our work, other than its well-known use in software analysis. You should read the paper if you're interested in the details. We also have our benchmark data in the paper. Please scan the QR code to download a copy. Thank you all for your attention. If you have any questions, feel free to ask me.
All right, any questions for our speaker? Come up to the mic. I will start. So you showed two primitives that are supported in your grammar of like all tokens must be on the same line and then tokens must be along the same column.
Let me turn to that slide first.
Sure. And I'm wondering, I guess, how expressive these primitives are in capturing the space of layout-sensitive languages. Like I know, for instance, in Markdown, they have cases where you can indent a certain amount, and then the next line must indent exactly that much, or sometimes a little bit more, a little bit less. Like, do you have a sense of how expressive this is? Can this capture kind of most layout-sensitive designs that exist in the world, or would you need more primitives for that?
So your question is about whether it's possible to extend the primitives to adapt to more layout-sensitive languages. And the answer is another big yes, because we actually encoded those layout constraints with the first-order logic formulas. So in theory, you can actually edit our tool to implement your own layout constraints, so long as it can be expressed with SMT formulas.
Okay, great. Any other questions? All right, well then let's thank our speaker and grab some coffee.
Thank you so much.